that both John and I, when you go to our things, our opposite numbers come up. So my long, most favorite, perhaps collaborator, is now almost there. You there? Are you almost critical for the scale of that?
Is this an introduction?
That looks pretty good.
Okay. Sorry about that.
So John Sullivan talking about what it says on the screen.
Okay, thank you. So first, quick ad for the Berlin Mathematical School. If you have anyone who wants to go to grad school in math in Berlin, please send them to us. Applications on the web for next fall. They're due in 10 days, but otherwise. Yes. Yes. So unusually for Germany, we start with 2 years of coursework. So I probably don't need to explain what rope length is here. The thickness of a space curve, also called its reach, the distance to the medial axis, it's the radius of the largest embedded normal tube around the curve. Rope length is length over thickness. Really, the idea of reach goes back to Federer, and he sort of has this general idea that positive reach should mean a C11 submanifold. Of course, it might have different pieces of different dimensions, and it's a little complicated, but for the curve case, it's certainly clear. Positive thickness means you're an embedded C11 curve, meaning your tangent vector is a Lipschitz function of arc length. And a simpler related problem is the Gehring thickness, simply the minimum distance between two components in a link. So a few cases, rope length minimizers are known. This goes back to a paper a long time ago I wrote with Rob and Jason. Like this simple chain connects some of Hopf links. The end components are circles, and the middle components are stadium curves, a half circle connected, two half circles connected by straight segments. So this shows that minimizing rope length does not produce smooth curves. These curves are not C2. Of course, they're C11 because they have positive thickness. And our theorems there used, we sort of had to span each component with a minimal surface to prove that this was actually, you couldn't do better than this. And some of the things in our family, the minimizers are not unique. Here's a more complicated thing. Again, this specific family where we know we have the minimizers, each component is a planar curve, linking a few other components. And once you get to one component linking four others, even the shape of a single curve is not unique. The examples, like I showed before, you can rotate some components with respect to others. So we can't expect uniqueness of minimizers. And what I want to talk about today is criticality. So what we have is a balance criterion making precise the intuitive idea that the tension force inside a component has to be balanced by contact forces. So maybe I'll just, there's a piece of chalk. If I have an arc of a curve here, and if I snipped it at some point P, then the net force that either side is exerting on the other is just the tangent vector. So one half pulls on the other half by this tangent vector. So if I have another point Q and a different tangent vector T1 here, minus T1, the net force on this subarc is T1 minus T0, or the change in tangent vector. And if this is somehow supposed to be part of a rope length critical curve, then there have to be other points somewhere here with struts, pairs at distance 1, so that, these struts can exert a force, and the net strut force on this subarc has to be that change in tangent vector. So this picture is illustrating how the struts work in this simple stadium curve example. The two end components are round circles. They have struts to a single point on this curve S. This single point, the whole circle, makes no net force on this point. But how does the stadium curve work? Well, this semicircle, all its struts connect to the single point C2 on the component C2. this semicircle, its struts connect to the single point C1 on the component C1, and there would be force pushing those two in. There's one more strut in the picture from point C1 to C2. That has a whole bunch of force on it. The other struts are in continuous families, and the strut measure is spread out over these families. This one strut in the middle has a delta function of curvature. So the criticality, these links, these simple links where we know they're minimizers, are minimizers either for the normal rope length problem or for this Gehring variant where you just care about distance between components. That case where there's no curvature bound is technically a lot easier, so that the criticality theory was in a paper 6 years ago now, and the rope length case is in a paper that's just been accepted, will appear very soon. So what can you say about knowing the criticality theory? What can you say about regularity of critical curves in the Gehring case? Well, of course, we're talking about finite length curves, so they're automatically Lipschitz rectifiable curves. Gehring critical, we can show, implies that the curve is C1 and finite total curvature. So the tangent vector is continuous function on the curve and of bounded variation. So one problem that we considered is the clasp. If I have two ropes clasped to each other like this, you might expect after that last example that we would see two semicircles, but there's nothing analogous to this strut. If I have two semicircles, the entire force of the one component is just touching the tip point on the other. And so that's not a critical point for the clasp, where I have one rope attached to the ceiling, another attached to the floor. I pull them against each other. This core curve is plotted as accurately as possible. It has infinite curvature at the tip here. It shows that your eye is not very good at picking out curvature. Right, what's that? No. This is accurately plotted. And here you see this little white area. This is the tube around the other component. That little white area shows that the tips of the two components are 6% further apart than they would be. So this, we have an explicit solution in our paper. The dashed line is the contact line between the tubes around the components. Explicit solution involving elliptic integrals. It's 0.5% shorter than the naive clasp you'd build with the semicircles. But as I said, the curvature is unbounded. It's the tangent vector is Hölder continuous, not Lipschitz.
What is it that you minimize?
Length.
The length
Straight's different.
of that black line?
Yes.
Wouldn't that be shorter if it was circular?
No.
No, because it can pull in. It can pull into the sides. The tips, take two ropes, clasp them against each other. The tips move apart, but they can pull in. You can write down for yourself a variation where you just replace the semicircles by ellipses, and as the ellipses get a little taller, then you can move in a little bit. The tips are further apart, but it's very surprising. So
Just remember, the constraint is no longer, just the distance between the two ropes is at least 1 or 2 or whatever.
So another link for which we can write down explicitly a critical configuration, which we expect is the minimizer, but we don't have techniques to prove it's the minimizer. We just can't imagine anything else that would beat it, and this is certainly a critical point, is the Borromean rings. 3 components in 3 perpendicular planes. It has the maximal possible symmetry for the Borromean rings, pyrotahedral symmetry. It's piecewise smooth, and again, some of the pieces are round circles, but other pieces are these arcs that we saw also in the clasp, described by elliptic integrals. So there are 42 pieces in total when you rate this as a piecewise smooth curve. Oops. So yeah, as I said, it uses arcs of the kinds of curves we saw in the clasp and circles. It's less than 0.1% shorter than a sort of close nearby naive configuration built just out of circular arcs. And because this one has curvature less than 1 everywhere, it's actually also rope length critical. So the clasp I just showed you had unbounded curvature. It's not for the rope length problem, it's for the Gehring problem. But as I said, we just recently finished the paper with the balance criterion for general rope length. And here's the statement of our theorem. Assume the curvature is a regulated function on the kinked arcs. That's a kind of technical assumption we wish we didn't have to make. Then a link gamma is rope length critical if and only if it has, again, a strut measure, the places where two components or two strands are exactly distanced one apart. You can put arbitrary positive force pushing those points away from each other. So a strut force omega. And before we sort of, for the Gehring case, I could have written this, the derivative of the tangent vector is strut force. But here we have a curvature bound. And so, when something's up against the maximum curvature, is not allowed to curve more than curvature 1, then we have to have some kind of force balancing that. And so what we have is a kink torsion function, or it's supposed to be kink tension function, phi, sorry for the typo, which is supported on the place where the curvature is 1. And we define what we call a virtual tangent vector, 1 minus 2 phi times t plus the derivative of phi n. And it's now this virtual tangent vector whose derivative is omega. So what does this mean? Well, let's consider the simplest case. I take some rope and I try to pull it down, but it's not allowed to curve more than a certain amount, right? What will the shape be? It'll be straight, then a circular arc, and then straight again. Fixed endpoints, minimizing length, but I can't, fixed endpoints and directions. This thing, I don't mean fixed endpoints. This configuration, straight, circle, straight, can be balanced by force just in the midpoint. I sort of pull down, I don't have enough hands here, but I pull down and out, and I push up just in the center. So this straight, circle, straight configuration, I have, here's my virtual tangent vector equals the tangent vector. Here, virtual tangent vector equals the tangent vector because the curvature constraint isn't active. Here, the curvature constraint is active. And I can balance this just with a single strut force in the middle. So by this equation, that means v is constant on this half of the curve and constant here. So v is just constant and jumps. And the difference in v here at this point is the strut force I need to apply there. And so here's some technical things we can conclude about smoothness. As applications, we can do clasps with various stiffness. That means you can artificially set a higher, a more restrictive bound on curvature. And you can have the clasp not go up straight. So you get very complicated things with little tiny straight segments, a kinked arc at the tip, a shoulder circular arc here, balancing the other guy's kink, and an arc of the Gehring clasp in the middle. We can list the whole family, a two-dimensional family of critical curves with no struts, where they're entirely kinked. And that goes back, that's a family that's been described in a different context by Hector Sussman. So let me just concentrate for a moment on the planar case. So if you take that equation I had, and on an arc away from struts, as I said, this virtual tangent vector is constant. So what does that mean? If I look at the equation and I put in what n prime is for a planar curve, no torsion, it's just t. So I get this simpler expression for v, and v is constant away from struts. So it reduces to this differential equation, has obvious solutions. So that means here, the phi function that I need to create this virtual tangent vector that we know has to be constant on either side phi is supported again only on the kinked parts. Phi is like 1 minus cosine type function. It starts here, phi equals 0 equals phi prime at the end of a kinked interval, and then again there's a piece of a 1 minus cosine type curve. So phi is piecewise smooth like this. At the endpoints, it has value in derivative 0. In the middle, its derivative jumps. So that jump in the derivative of phi corresponds to this atom of strut force. So what is the geometric meaning of this phi? Well, suppose I have 3 adjacent points on a circular arc, P, P plus, and P minus. I can draw rays into the center of the circle. And again, if you think about a curvature constraint, it's meaning if I try to bend it more, the curve will push back on me. So I can think of a force that can act. If I try to pull in, the curve will push back like this. And if these two vectors, say this angle is epsilon, if these two vectors push with strength 1, then this must pull with strength 2 cosine epsilon, which is like 2 minus epsilon squared. And so what is the net force at P, at a single point? If I have a bunch of these triple struts, I call this a triple strut. So if I have a bunch acting, well, the one that, this was supposed to be P minus, the one acting on these 3 points will touch P, the one acting here, and the one acting here. So I have so I need to tell you the interpretation. Use triple strut at P with strength phi of P. And so then the net force at P is, well, phi plus phi minus from these other triple struts that push at P, minus phi times 2 minus epsilon squared. And this, of course, is epsilon squared times the second derivative. I guess also with a minus sign. So anyway, then I have, oh no, probably with a plus sign, and then here minus minus is a plus. So the epsilon squared is the same factor. That's where the phi double prime plus phi comes from. And so the other thing I just wanted to say is that if I snip the curve here, remember I said if I cut a curve, what force do the two parts pull on each other with? Just the tangent vector, tension 1. But if I snip the curve in the middle of a kinked arc, then the force that one side exerts on the other is really this virtual tangent vector. So this curve under tension, what's the force that this part is exerting on that one? It's the virtual tangent vector. And I'm sure I'm out of time. Yeah, sorry for the technical difficulties at the beginning. I'm sure. So you can recover v. I mean, we had this equation. What is v in terms of phi? If I just think, cut the curve here. Well, there are only 2 triple struts that transmit force from one side of this cut to the other. That's this one and the one here. And so that's why you get the net force. The 1 times t is the regular tangent vector, and then the rest of it is just the net force exerted on one half by the other due to those two triple struts. So, thank you.
Given the technical difficulties, I thought it was fair to let John know. Questions? Yeah, Pedro.
You wrote in your theorem that you have the curve on C2 on this region where phi is bigger than 0, right? Theorem.
Yeah.
So my question is it just C2 or is it C infinity here?
Well, so the curve is W3
This is
BV, but if I have an atom of strut force coming in, phi prime and tau may jump. So here I had an atom of strut force coming in, and it was phi prime that jumped because the atom of strut force came in the principal normal plane. If an atom of strut force comes in the binormal plane, that's going to cause the torsion to jump. We actually have the other comment is we have examples of sort of strut-free cases which are like this. So here, this is one kink dark, this is another kink dark. They're coplanar. It's not C2 across here, but of course, as in my example over there, phi vanishes at the boundary. So the statement is C2 on the set where phi is greater than 0. So this is the kind of thing that can happen even without struts. With struts, we expect when strut force comes in perpendicular to the osculating plane, then torsion will jump. Yeah.
Further questions? Okay, we can continue during coffee, which will begin now. Let's thank John again.